Lesson. Today we are going to study DFS. In our previous lesson we studied BFS, breadth first search, which we were exploring the tree level by level. For example, if we consider this as a tree, first we check this level, then second, and then third, and this way we continued until the last level. However, today we study DFS, which it is also a tree traversal algorithm that explores the node of a tree by following each branch as deeply as possible before backtracking. So instead of finishing level by level, it starts from the root node and it goes either to the left or to the right. It goes until the last node in the tree, to the leaf node, and then start backtracking. So let's write this same example that we used BFS, and now I'm writing this same example with DFS as well, and let's see what are the differences. The main difference, or the first difference that you should remember and memorize, that is that how they work. For example, in BFS it explores the tree level by level, and we use a queue data structure to implement that approach. However, in DFS it starts from root and it goes as deep as possible, and with that approach, to implement that approach, we use stack. That is the main and big difference. Okay, let me write this is the same example, and I name it DFS, deep first search. Okay, so with DFS, or breadth first search, or deep first search, we use a stack. Let me first draw a stack here. Okay, let's say it's our stack. So first I create my stack. Const stack equals, so and immediately we insert the root node inside our stack, this dot root. That means A is added here. Okay, so we added A in the root node, and now we start checking every node, extracting them from this stack, and we continue that process until the stack is not empty. Okay, so I'm saying while stack.length is greater than 0, you continue processing. So every time we remove the last node from the stack, const current equals stack dot pop. We use the pop method to remove the last node from the stack, and now we have one node in this stack. So if we remove this, that means we remove that one node that we had inserted in the stack. Once we remove that from the stack, then we start processing this. That can be any process. For example, if you are looking for a specific node, then now we can check or we can do whatever process that we need on the current node, which is just extracted from the stack. Once the process is done with that node, so we say now we have to add its children. Right now we process node A, so we check if the node A has right or left child or not. If it has, then we have to insert their children as well. So I'm saying that if the removed node, which is current dot right or dot left, doesn't matter. For example, I start from adding the right side. If it has a right node, a right child, add that to the stack. So stack dot push current dot right, and also we need to check its left child also. So we say if current dot left. If it has a left child, that we see it has a left child. For example, at this point, when we check, does this A have a right child? Yes, we see it has. So we add this right child to the stack. So we add that here, that is C. Okay, we added that here. And now also we check, does it have a left child? So we see, yeah, it has a left child also. So we add this also to the stack. So we say stack dot push current dot left. So with this operation, we add B also to the stack. Okay, now B is also added to the stack. And our process continues. So it's this time it says, is length greater than 0? Yes, now the length is 2. So if the length is 2, we remove or extract the last inserted node, which is B. So I remove that now. And now when I remove that, I start processing that. I do whatever process I need. And then once I remove that, now I check, does it have a right child? So we see B. Does it have a right child? Yes, here it has a right child, and that is E. So insert that to the stack. Okay, now insert that to the stack. Okay, insert it. Also, does it have a left child? Yes, it has, and that is D. So let's insert that also. Okay, D also inserted to the stack. So now the loop continues. This time length is 3. Again, it is greater than 0. So we extract the last inserted node, which is D, and we remove that from the stack. And now we do our process here, whatever process that can be. And then check, does it have a right child? So D, it doesn't have a right child. It is the last one. How about left child? Does the node D has a left child? It doesn't have a left child also. So the loop continues. This time it checks the length, and the length is 2. So again we extract the last node, and that is E. So that is E here. Now we do our process and then check, does the E have any right child? We see it doesn't have. Does it have a left child? Also it doesn't have. So the loop continues. Now here the length is 1. Again, it is greater than 0. So we extract or remove the last inserted node, and that is C, the last inserted, which are left in the stack. And now we delete that also. So now we do our process here, and then we check, does the node C have a right node? We see it has, so we insert that to the stack. Okay, insert it. And how about the left child? Does it have a left child? We see it doesn't have a left child. Again, the loop continues, and at this time also the length is 1. So we extract the last node which is in the list in the stack. We remove that from here, and now we process that, and then we check its right and left, and we see that it doesn't have any right and left. It is the last one. So this way we could visit every node in that tree. I hope it was useful enough. However, if you have any questions, you can add them in the comment, and I will come to them with a new definition, a new approach, and new examples. Have a nice time.